This will be your one and only lesson here for Chapter 5 stuff. This is all about reciprocal functions, or what we would call rational functions. This is the way you would have heard it in the past. Algebra 2, we do a whole chapter on rational functions. And all that simply means is any function where you have x in a denominator, so on x on bottom of a fraction. So that's why they also refer to it as a reciprocal fraction. Obviously, the reciprocal of x over 1 is 1 over x. So you can refer to it either way, but rationals are the way you would have heard it in the past. So just a couple things on that. If you were to take an inverse, so here's the general look of a rational function or a reciprocal function. If you were to do the inverse on this, so remember, inverse is where you switch x and y. So you got the x here now and the y here. Well, if you were to get y by itself, you get back to the original look. So this rational function look is actually an inverse of itself. You get the exact same result when you take the inverse. When you graph them, so this is just like a parent function graph for y equals k over x. So if you had no other number in there but y equals 1 over x, this is the general look that you would get. So a couple basics that we're going to be talking about for this section. One would be asymptotes. So remember that an asymptote is a line that you are approaching but never actually land on. So my vertical line is at x equals 0. So right here you're seeing at x equals 0. This is the line that is being approached from the left and from the right, but we never actually land on 0 for x. So because of that, my domain, so it looks like these got switched when that was filled out, but my domain would be all x's, all real numbers for x except 0. And you'll see the other asymptote on this, the horizontal asymptote, is y equals 0. So you got a horizontal asymptote right here running through y equaling 0 is your other one. And again, from the top and from the bottom, you can see both graphs are approaching this line but never actually land on it. So because y does not equal 0 here in the parent function, for the range, you would get all real numbers except 0 for y. You got two axis of symmetries on this. Both dotted lines that you see are axis of symmetry, simply because you can mirror the graph across those lines and get its look on the other side of that line. So either way you look at it, with here's the y equals negative x, you can see if we were to fold this paper across this line, right, I would have two matching sides. Same thing if I were to fold the graph across this line here for y equals x, again I would have mirror images on both sides that would land on each other. Couple translations. We dealt with these earlier on in the year already, but if you take the general look, which is y equals some number over x, if you were to graph that, you would be pretty close to this look that you see right here, but when we put the +2 at the end, that's a vertical shift. So we are taking the whole graph and shifting it up 2 units. So here we go with that look. So you had a horizontal line originally at y equals 0 right here, but because we are shifting up, it's now at y equals 2, would be your horizontal asymptote. Remember, anything that is attached to x is going to affect your graph left and right. If it is not attached to x, if it is out here by itself, then it's going to affect your graph up and down. So just remember, that's just a basic rule from what we did earlier on this year with translations. Here we are with a horizontal translation. So remember, here's kind of the general idea. This is attached to x, so we know it would affect our graph left and right. The x's are always kind of backwards of what you would expect, because the negative that you see here is kind of built into the format. So it's always the opposite of what you think on that. So in this one we have a +4, but instead of going in the positive direction, this would shift our graph left 4 units. So we get this look here, where we're shifted left 4. So remember, in the parent function graph, you get a vertical asymptote at x equals 0, is originally this line right here. It is now shifted to x equals -4 right here, simply because of the +4 that you see on that one. Here's kind of the explanation as to why it's -4. Remember, you can never divide by 0, so we always see the boundary line or the asymptote as any number that we cannot use or cannot get out of this function. So I'm not allowed to use -4 on this, because that would create a 0 in my denominator. So that makes -4 a number we cannot use. So domain would be all real numbers except for -4 because we can't get a 0 in our denominator. So that creates the asymptote that we see right here. Notice the horizontal stuff was not affected. So you got your horizontal asymptote still at y equals 0. You got your range still at everything except 0, because all we did was affect our graph left and right, not up and down. And then that was just a reminder right here as to where we saw some of these things earlier on in the year. All right, last part of this. So here's cases where you'd have x on top and on bottom for some of these. So remember, like we just mentioned a minute ago, you can never divide by 0. So anything that would create a 0 in my denominator is a number that we cannot use. So if I take my denominator and set it equal to 0, right, we would always take that path for solving for our vertical boundary line. Our vertical asymptote is going to come from that look here. For the horizontal asymptote, this was tried to be explained through like an inverse process to show you where this is coming from. But simply stated, if you have an x on top and on bottom, as long as they have the same exponent, then all you have to do is divide their coefficients to get the horizontal boundary line, or your horizontal asymptote. So in this case, if this is x to the first and this is x to the first, then I can just do a divided by c to get my horizontal boundary line that you're seeing right here. So it's a over c. If these exponents are not the same, the rule is if the top exponent is bigger than the bottom exponent, then there is no horizontal asymptote. If the bottom exponent is bigger than the top, then it's automatically at y equals 0. You can take advantage of a calculator for some of this stuff. If we were to sketch a graph, if this is a case where you do have access to a calculator, take advantage of that. So just keep in mind that if you were to put this into your y equals setup for your calculator, you got to be careful and make sure that you put parentheses around everything that's in your denominator, or your calculator may read this wrong. Depends on which calculator you're using. But it's always safest to put this denominator in parentheses just to make sure your calculator can read it properly. So what we're just looking at up above, as far as the asymptotes go, so your vertical asymptote is always x equals something. In this case, if you set your denominator equal to 0, that's what you're seeing right here, then you get this result for the vertical asymptote, which, by the way, is good to know how to do by hand. Even if you're using a calculator, you may not be able to figure this out on your calculator. So this is kind of the approach that you want to be familiar with. Notice that if this is an asymptote, then when it comes to our domain, we can use every number except that for the domain. That's a number that I'm not allowed to plug in for x. Same thing with the horizontal. The easiest way to see this, again, is just to do the coefficients. So because this is x to the first and this is x to the first, I just take the coefficients and divide them. So I got a 1 right here, I got a 3 right here, so 1 over 3 is our horizontal asymptote. And so for the range, we can use all y values except for 1/3. All right, getting into the last part here. Again, you can try this one on your own. This is the exact same idea as number 1 that we just explained. So I would say give that one a shot, and then you can check the math over here to the right and make sure that you are doing those properly. But that would be the same explanation as what I just gave right there for number 1. Just one idea to throw out there. This is something that we're going to run into again down the road, is the idea of a limit. When we kind of introduce the calculus stuff, it usually comes by way of limits. Is usually kind of the introduction that you get when you get into calculus. A lot of it can be explained with limits. So in this case, just to give you an example of that, you can see that as we move to the right, so as you follow this graph, so as your x's become larger and larger and larger, or in other words, as x approaches infinity, you can see the result that we are approaching is 5 over 2. Right? We would never actually land on 5 over 2. It's just the number that we get closer and closer and closer to as x approaches infinity. So as x gets bigger, we get closer to this result, so we say that this is our limit, simply meaning that it's the number that we are approaching as x approaches infinity. So just to kind of show you that really quick on something like example number 2 right here. So if you were to look at this, so imagine for a minute that I started taking extremely large numbers and sticking them in here for x. Right? That would make these numbers over here insignificant. Right? If I start using really, really large numbers for x, if I throw a trillion in there and a trillion in there, so you can see if this were 5 trillion minus 3, and this were 2 trillion plus 8, so this is just barely bigger than 2 trillion, this would be barely smaller than 5 trillion. Well, if I were to reduce 5 trillion over 2 trillion, I would have 5 over 2. I'm not going to land exactly on 5 over 2 because of these numbers right here. Right? But as that number becomes really big, I get closer and closer and closer to 5 over 2. But because of these numbers, I would never actually land on 5 over 2. It's simply the number that we are approaching. We get closer and closer and closer to it, the bigger this number becomes.